Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Allahumma aftah alaina hikmataka wa anshur alaina min khazaini rahmatika ya arhamar rahimin. Alright, so today will be the experiment number 7, study of an RC phase shift op-amp oscillator. Okay, so the objective of this experiment, we will learn about how an RC will change phase or phase shift by connecting it to an op-amp, and then the result will be a signal, sinusoidal signal or oscillator, and then how to measure the frequency of this oscillation. Because we are dependable on the R and C values, we will use the RC formula using 1 over 2 pi RC square root 6. Okay, the R here will be a couple R and C with the same values, and R and C, which we will see later. Okay, so how to measure the gain? Basically, we can measure the gain by identifying what is the feedback resistor RF, and also the R. Okay, the R is the one that being used for the RC. Okay, so at least you have to get 29 as the gain. If it's less than that, your signal will be damp oscillate. That means it will not maintain the oscillation, but it will become like this. This is if less than 29. Okay, for more than 29, we will ensure that the oscillation is stable, sinusoidal function. Okay, maintain the amplitude here. Okay, alright, so basically this is a simple block diagram to explain the feedback linear oscillator. Okay, so the amplifier is op-amp amplifier. So this is the output. The output of the amplifier will be the feedback network to the input. Okay, so this one is the part of the RC. Okay, so basically we have RC network as a feedback, and then the output of the amplifier will be the input from the feedback. Okay, so since we have RC circuit or RC series in this experiment, so we will incur, or the phase shift will occur with the 60 degree each. Okay, so since there will be 3, first is 60 degree, second 60 degree will become 120 degree, and the third one will be 180 degree. So how do we know it's 60? We use this formula to find the impedance of the capacitor. Okay, so from there we can calculate the phi. Phi is the phase shift. Okay, so it can be other values also, but in this experiment we will substitute what is the C and R and prove that it can have this 60 degree phase shift. Okay, so for first phase shift 60 degree, we will see in the oscilloscope the input and output shifted like very small, about 60 degree. Okay, when it come to the second RC, it will become 120 degree, and then when it comes to the third one, it will become 180 degree. That's mean inversely, one is like this, another one is like this. Okay, 180 degree. The full is 360 degree. Okay, like this one, yeah. The input and output using the 3 stages. Okay, so this is 180, this is 360. Okay, so this is the circuit diagram that you have to construct. Okay, in the face-to-face lab, we have this one to actually to test, okay, to experiment which values will be the perfect sinusoidal. Okay, if the values is less than it, it will be damped and also cut here. Okay, so we don't want like that. We want a full sinusoidal wave. Okay, so this is the RF, the combination of this resistant and this resistant. And this is the R. Okay, R1, R2, R3 or equivalent to R. So the gain will be the RF divided by R. So here, let's say we use, actually the advisable is you use the maximum. Okay, 320 divided by 10K. Okay, so you will get 32 as the gain. Alright, so the minimum you must more than 29. So this is the first stage RC filter, second and third one as the feedback of the amplifier. So this amplifier. Okay, so it will be powered up by a DC supply of 12 volt. Okay, so it will be powered from to this amplifier, but not as the input. Okay, no DC here. Okay, so you will have the sinus oscillator, you will have a sinusoidal, or maybe you can have also triangle and square wave, depend on the setting. Yeah. Okay, so this schematics is for your PSpice. Basically, you in the values of plus and minus in the PSpice is different from the figure that I've shared just now. Okay, so be careful with the label. So since this is a negative port here, so this is called negative feedback. Okay, so the V out is measured here. Okay, and the V in measured here. But since later we want to see the phase shift, you have to put a marker here to read the voltage at first point C1, C2 and C3. Okay, so these three places will show you that the first one will shift 60 degree input output, the second one 120 degree different from input and output, and the third one will be 180 degree. Okay, so to ensure that your schematic will be functioning well, okay, so at the IC there is an initial condition. Okay, so you change into 1 milliamp. Okay, so just put the parameter inside the IC here. Yeah, IC capacitor current IC. Okay, and then to ensure that you will see a signal that can be measured. Okay, not like very small like this, but rather you will get something that can be readable like this. So you have to make sure that it is very short. The time, okay, the time will be equivalent to F 1 over T. Okay, so how do we know? We know the RNC, and then we know the formula F1 over 2 pi RC square root 6, right? Okay, so from here we can know what is the F. Okay, so to identify the time, you will use this formula to estimate. Okay, but this one is for only one period. Okay, so if you want to see like 1, 2, 3, 4, 5, maybe 10, so you have to multiply by 10. Okay, so that's why we got the 1.6 millisecond here to see 10 oscillation in one window. Okay, one oscillation is equivalent to 1 over f. Okay, so this will be your expected result. The red one is the input, okay, and the green one is the output. Okay, so if you can see, this phase shift is different. So it's 180-degree phase shift. Okay, the phase is shifted. Okay, so if you want to see a better measurement, so this is also the input and this is the output. Okay, so you can see that one is negative, one is positive, the phase. Okay, and then the value of the input, this is from the V in. Okay, we mark at X just now, and then this is the output after the amplifier. Okay, so if you see this one, there is a spike here, so it might be because of the current. Capacitor injects a current. Okay, we consider this is noise and that's fine. Okay, just ignore this one. Okay, so another important point is you have to see the phase shift at different point, right? This is the output. Okay, this is the input, for example. So you want to see this one. What is it? 60-degree at each point of the RC. So this is the output. Okay, and then the point at point A, B, and C. Okay, so if you want to make it separate window, so you just go to the PSpice plot at window. Okay, and then you add trace. You find the trace that you have marked on your schematics. Okay, so now we have different window. So here you can check the trace and it will put at window. So the first window is at the first RC, the second RC, and then the third RC. Okay, this one the same one, VC also, and then this is the output. Okay, so when you compare the first RC, the first one, okay, you can put a cursor here. Okay, and then another one is here. Okay, so you calculate. Okay, first of all, find the full time. Okay, for this one, from peak to peak, what is the maximum time? Okay, divided by how many boxes? So is that 60-degree? So check. Okay, so how many? 1 2 3 1 2 3 4 5 6 7 8. Okay, 8 is equivalent to 360. Okay, from peak to peak. Yeah, so one box you divided by 8, and okay, and then you see what is the value here. So it check with your simulation. And then the second one, okay, the second one, this one, and then it move here. Okay, so how much is it? Is it 120-degree? Okay, phase shift. So show that one also, and then this one and this one. Okay, this looks like 180-degree. Okay, so this is where you have to identify the phase shift. Okay, RC phase shift. Okay, so you can also, the next one, you can also check your theoretical and your frequency 1 over 2 pi RC square root 6. This is theoretical value. So for measurement value, you have to find in your graph what is F. So find by 1 over T. Okay, so this is 1 cycle. Okay, so how much is this one? The time 1 over 171.93 micro. So find the frequency, okay, and compare with the theoretical. Alright, so or there is one more way to do that is go to the trace, okay, here trace, and then there is a Fourier, okay. You can change from time domain to frequency domain. Why? We want to check the peak frequency here. Okay, so there are two ways to check the frequency by measuring the T, or you change to Fourier and check the F. Okay, I think that's all for the briefing of the lab by PSpice. The rest also can benefit it, inshallah. Okay, with that I finish with Tasbih Kifarah and Surah Wal-Asr.